Recording is started. So welcome to Thursday. A few things knock out the beginning here. This AP review quiz. You guys remember review quiz 1? You guys have had this for a while now. So I'll pick this up tomorrow. I'll grade this over the weekend. You guys, I bet a lot of you guys have this finished by now. So just turn this into grade tray either today or tomorrow, and I will grade this over the weekend. Okay. So, then other thing I have to talk about is talk about schedules with you guys. Actually, you guys were somebody did about this yesterday, so it's just real fast. Flash this up here one more time. So the old system was they used to pass around paper like this, had all the science selectives, check a box, and then I do something on my end. But the new system is you guys got to paper through your English classes, and you have to figure out yourself which science selectives you want to take. So at least I can use this, if nothing else, as a checklist. Right. And I think where I enter into this is if you want to take another AP class your senior year, just bring it up to me. I can sign off for you. I think you need my signature or something, but I mean, you guys are AP anyway, so you guys know what AP is all about. And so here's your AP options. If you want to take one of these other AP classes, then let me know. I can sign off for you. Remember, as a graduation requirement, between science and social studies, you have to have 7 classes. So you could do like 4 science and 3 social studies, or vice versa, but they have to add up to 7. Okay. Well, what other science electives do we got? You guys got these options: environmental science, marine 1 or 2, anatomy, forensic science. And you guys were telling me yesterday that science research actually does not count as a science credit. So, yeah, guess that's the case. But yeah, we've got a couple students here who are doing science research. So if you want to ask them what that's about, together a science project, present the all. Okay. All right, there you go. So you guys should have a course registration paper through your English classes. And if you need me to sign anything, or if you have any questions about anything to do with science classes, then at some point, then I'm glad to sign anything you need me to sign. All right, so what we've been doing this semester is we've been doing some EP review for each of the sections, one by one. And then here to remember my honors classes are going off learning all other cool things from physics. So I want to give you guys crash courses on what they're learning. And this week we're doing relativity. So let me see if I can in one day tell you guys all about theory of relativity, whatever I can condense into these 45 minutes. So we're going to go back to calculate how the speed of light was originally calculated. Well, I guess there's a story before the story. If you go back many centuries ago, one of the very first rudimentary calculations of the speed of light was there was this Danish astronomer, I think his name was Ole Romer, probably mispronouncing that. He was watching the orbit of the moon Io go around Jupiter. And he noticed that as Earth headed towards Jupiter, it looked like the frequency of that orbit increased by, I think it was like 13 seconds. And then as Earth was headed away from Jupiter, the frequency of that orbit decreased. Again, so it's something like 13 seconds per orbit. And he was, if you know the distance between here and there, and so there's effectively some kind of Doppler shift, you could calculate what the speed of light had to have been. And he got 2.2 times 10 to the 8 meters per second, which is not too far off from 3 times 10 to the 8 meters per second. Now, what was the first time we got 3 times 10 to the 8 meters per second for the speed of light? So that involves an experiment that looks like this setup, where we're back to 1849. 1849, there's a guy named Hippolyte Fizeau, and he did this right. He had this toothed wheel, so like teeth and gaps between the teeth. I'm thinking of tomorrow giving you guys this particular puzzle too. Right now, a bunch of extras. And then many kilometers away, a reflective surface, a mirror. So maybe there's like 3, 4, 5 kilometers between here and here. And then he would have, I actually got this drawn up ahead of time. So take a look at this one. He has some light source, represent that with a candle. Of course, this is sending out light rays in all directions, including maybe a light ray that goes through the gap in the teeth and then hits this mirror and then reflects back. And then here's an eyeball here. So you can see the reflection of light. Okay, so that's all fine and good, right? Now, light moves ridiculously fast, but it does have a finite speed. The fact that it has a finite speed means if you get this wheel spinning fast enough, because now he's spinning this wheel, think about what that would mean for what you would see in the reflection, because that reflection would change at some point. So some of these light rays are just hitting the teeth and not passing through at all. And so of course they never get reflected to start with. But what about the light rays that go through the teeth? Well, if this wheel gets spinning fast enough, then by the time the light returns back, say goes a few kilometers this way and then a few kilometers back, if this wheel is turned just a few degrees so that the teeth cover where the gaps used to be, then what would you see? Well, you wouldn't see the reflection of the light source at all. And if you can figure out exactly and what that would look like, say if you're speeding up, this wheel spinning like, it would look like a door was closing on that reflection. And right where the place where the light was exactly blocked, if you know how many teeth you have on this wheel and you know the distance to the mirror and back, you can calculate the speed of light doing just that. And he did the same got accurately 3 times 10 to the 8 meters per second. So we've known the speed of light going back to 1849. Now, it was assumed back in the day that I taught you guys a little bit about waves, right? You guys know how you can hear me right now is that there's a longitudinal wave, a compression wave going from me to you. And some waves are transverse waves and maybe also need to be, remember, I broke out the slinky one day, did some transverse waves. The transverse wave could be on a string. Earthquake waves, there are P waves and S waves are longitudinal and transverse. So it was assumed, just kind of as a matter of general knowledge, that, oh, of course, well, light probably needs a medium to travel on also. Now, nowadays, we know that that's not the case. Light can travel through a vacuum. But how do we know that? I'm going to bring in, I should skip this one for a moment. Let's go to Nicholson-Morley. So there's this experiment set up, Nicholson-Morley. This is in 1887. Oh, there's different versions of the experiment. This goes through different iterations, but let's focus on this one here, where they set out to figure out what is Earth speed relative to some luminiferous ether. Now, if you've never heard of luminiferous ether before, or you've never read about this in a science textbook, it's a good reason why. It's because this particular experiment that guide you guys through ended up accidentally proving that it does not exist. But this was assumed to be the medium that light would travel on before people understood that light could actually go through a vacuum of space. Now, why did people think there would be this luminiferous ether and that we could measure our speed relative to it and why that would be important? Well, think about the geometry of the solar system, say like the Earth spin. Here's the Earth, okay? North-South pole. Now the Earth is spinning about 1,000 miles an hour at the equator relative to the pole. So this is just spinning really fast. But that's not the only motion. Here's the sun off in the background. So think 3D, right? Got 1 astronomical unit from here. Here's the sun way in the background. The Earth is also on this orbital path going around the sun. Okay? And so it's moving through space really fast. But that's not the end of the story either. Our whole solar system, centered about the Berry point, which is near the center of the sun, is also moving around the Milky Way galaxy. So if you look at spiral arms of the galaxy from above, right, looks something kind of like this, like all the solar systems are moving around in a spiral. So you put all these motions together, and they figured that if there was some luminiferous ether that light waves traveled on, kind of like ripples traveling on water or sound wave traveling through air, that all these motions, you'd have to be able to account for them, and we'd have to have some relative speed. Right? That was the thought, and everybody believed this. Probably almost everybody. So this pair of scientists set out to determine what that relative speed was, and the way they did that, they set this experiment was this way. They had this type contraption. They had a light source here. I represent with a candle, but some kind of light source that was sending out light beams, and maybe one light beam was traveling, say, along this arm of this contraption, something like this. And here at 45 degrees, they have a splitter. well, I'll say a half silvered mirror, also called a splitter. Okay. And what that would do, well, half silvered, the light ray could travel through it, but parts of it, if you give a chance, it actually gets reflected off at a 90-degree angle, right, bubbling, something like that. And say either goes down this arm or this arm. Okay. And then each of these arms was the same length, so this length is equal to this length. Okay. There'd be a mirror on the back end, and the light beams would each be bubbling, reflected back to the half silver mirror, where either like part of this one should pass through, and this one should bounce off at 90-degree angle and pass this way. So you'd have two light beams that reach finally this endpoint destination. Say you have like a card here, like this. And they took two different paths to get to this card, right? So one path was through and then back and then bounce off this way. The other one bounced off first and then went through this way. Okay. Now, if the distances are equal, you might say, well, shouldn't it take the same amount of time for those two light rays to meet there? And then if they had some kind of interference pattern, then they should just be in sync with each other. So just be all constructive interference, and maybe you shouldn't get anything too special. Okay. But these scientists thought that they actually would reach the card at different times, and I'll show you guys why. So hold on to this idea, because I'll show you guys a slide that we're going to come back to this. This goes back to a problem that I remember studying for the FCAT back when I was in high school that really intrigued me. It was like two guys having a race around, here, let's do like a start finish line here. And so, so you got a couple of guys, and let's say they race each other, and they're both pretty close speed, so it's going to be a pretty close race. And they say, what we're going to do is we're going to race around this tree and back, but they have different strategies. So one guy says, I'm going to pace myself, so I'll go 10 meters per second there and 10 meters per second back. And the other guy says, well, maybe I'll have a variable speed strategy. So for the first half of the race, I'm going to go 15 meters per second, and then round in the tree, maybe really winded now, so I'll come back like 5 meters per second, something like that. Okay. Now, which guy's going to win the race? The guy that paces himself and goes 10 and 10, or the guy that sprints first, goes 15 and comes back 5? Okay. Show of hands. How many guys think the guy, somebody wins that race, they don't tie? Okay. Who thinks that the guy that goes 10 and 10 wins the race, paces himself? Who thinks the guy that sprints first is going to win the race? Okay. So let's put those numbers to it, give them a distance. I'm going to also alter this one more small way. I want to give you guys that story first, because maybe it's a more direct way to look at the story. But you could attach a slightly different story to it, which is going to be closer to the Nicholson-Morley experiment, which is the guy that here, instead of them doing a foot race, what if instead you had a lake versus a river? So to tell you, you'll have two stories you could attach to this situation. They're mathematically identical, and then just go whichever story you like. But let's say this river has a current, let's say speed of the river current is like 5 meters per second. Okay? And what if these guys, instead of running, were in a boat race? Okay? And I like the story with the water because it's closer to the luminiferous ether type story. So whether they're running or they're boating, okay, either way, they're going to have a race to the tree and back. So attach the numbers. Let's say the distance to the tree is like 150 meters. Okay? And either the guy is pacing himself going 10 meters per second there and back. Well, that'd be like being in a lake in the boat going at, let's say the view of this boat is probably like person A and person B. Okay? It could be like 10 meters per second. Okay? So maybe you're just in a boat. But the guy that sprints first, 15 meters per second, and comes back at 5 meters per second, that actually would be sort of analogous to paddling as far as you could both ways in a boat on the river, where part way you get a boost from the current, and part way you're fighting the current. So if this guy can row the same, then doesn't he go down current, getting a boost at 15 meters per second? And he comes back, because 10 plus 5, and he comes back 10 minus 5, which would be only 5 meters per second. Okay. So Okay, all right, so how much time does it take each of these guys to complete the race? Because whoever takes less time is the winner of the race. Right, so we can just do distance equals speed times time. Now, the guy that paces himself or is boating in the lake, so he's going to go round trip 300 meters at 10 meters per second. So 300 meters at 10 meters per second. You guys see the time is going to be 30 seconds. Okay, so the lake or the guy pacing himself takes 30 seconds round trip for that race. How about the guy who either sprints or is in the river? Well, I need to split this into two parts, right? Downstream and upstream. So downstream, he's got x equals vt. He's going 150 meters at 15 meters per second for some time. And it looks like that time would be, what is that, 10 seconds? Okay. And then he's going to come back 150 meters, but at only 5 meters per second, because 10 minus 5 or right, for some time. And that time looks like what is 150 divided by 5? I think that's 30 seconds. Okay. So if you added those two legs of the trip, that's a 40-second round trip. I say 40 seconds. Okay. So do you guys see the guy that paced himself or was in the lake with second one who wins the race because it takes him less time? Yeah. Yes, sir. All right. So let's go back to Nicholas and Morley then. So remember, they have this model in their minds that, well, the Earth is spinning and going around, revolving around the sun, and the sun's probably moving around the galaxy. And if all that is true, then there's got to be some relative motion to this supposed hypothesized luminiferous ether. Okay. And so suppose, and nobody knows which direction it's going, but maybe suppose it's going in this direction. Hypothetically, somewhere. Okay. If that's true, then whatever light beam travels along this arm of this rate that they made, that's sort of analogous to paddling on the boat, where your speed is not affected by the direction of the luminiferous ether. But if you go on this leg of this arm of the rig, that's sort of analogous to paddling on the river, where partway you're fighting the current and partway you're getting a boost from the current. And it's going to take longer for that to happen. So by the time these two beams meet up at this end destination, at this card, there would be an interference pattern showing that there was a difference in speed because the waves would be out of phase. Okay? So that's what they thought they would see. They set up this rig and they got nothing. The result they got showed that the speed of light was the same regardless of the motion, which they thought, okay, that's weird. But then, oh, well, maybe that's not a big problem because we can just take this and turn this 45 degrees or 90 degrees, or maybe we can take this to different latitudes. Maybe we can wait at different times of the year when Earth is moving at different. It didn't matter what they did, when they did, how they did. They always got that the speed of light was constant no matter what. And actually, weirdly, they weren't expecting that at all. This is sometimes called the most successful failed experiment in science because it disproved the luminiferous ether, but it also proved that the speed of light is constant regardless of your frame of reference. There is no such thing as luminiferous ether. The speed of light is always the same. Now, around also that time, 19th century, was James Clerk Maxwell, who wrote these four equations describing all of electromagnetism. And this is beyond the scope of this class, but if you guys do like physics 2 or graduate level physics, you'll see these electromagnetism equations, four really famous equations. And embedded in these equations is the speed of light. You guys see the speed of light, 3 times 10 to the 8 meters per second. And that also represents a constant. So that Michelson-Morley experiment showing that speed of light was constant was consistent with these equations, but nobody could quite wrap their minds around how that could possibly be. Well, maybe this speed of light is constant relative to this luminiferous ether, but now Michelson-Morley just proved that there is no such thing as luminiferous ether. So that's so 19th century closes. Nobody's quite sure what to make of this. Then comes along the 20th century, and Einstein is over working at a patent office in Switzerland. So he's just all day, every day thinking about how do things go together, how do things work, cross-checking patents, seeing everything that's been submitted to the patent offices in the past. And he's thinking really hard about Maxwell's equations and Michelson-Morley, and he realizes the answer to this problem. He catches something that he applies the correct interpretation that nobody else had figured out up to this point. So draw this for you guys. Suppose, yeah. Actually think about questions like, what if you were to travel along with a ray of light? What would that look like? Sure. Before I draw something here, but let me just drive a point home that I've been kind of trying to make, but just make sure you guys get this. Okay? Suppose there's like a vehicle in motion, okay? And the vehicle is in motion with a speed of 10 meters per second. Okay? And you're standing on this vehicle and you got a baseball and you throw the baseball at like 20 meters per second relative to you. Like that's your throwing speed. Your throwing speed is 20 meters per second. If there's a guy off on the side that has a radar gun, what's the speed of the ball going to be according to this guy? What do you guys say? 30, right? To 20 plus 10. Or if you threw the baseball backwards, you do 20 minus 10, right? So that's called Newtonian relativity. So it is a form of relativity. It's just relative motion, but it's Newtonian relativity. That's every. I mean, that's applicable to like AP Physics 1, right? 20 plus 10 is 30. Right? But here's a weird thing that you can draw from, say, Michelson-Morley or is if this car turns on its headlights, and you measure the speed of light of, let's say break out that tooth wheel like I was showing you with the Fizeau experiment. If you are along for the ride, you calculate the speed of light is 3 times 10 to the 8 meters per second. But if you're this guy off in inertial frame of reference, you also calculate the speed of light is 3 times 10 to the 8 meters per second, regardless of how fast the vehicle is moving. Even if the vehicle is moving at like half the speed of light, both of these guys would agree that the speed of light is exactly the same number. Okay? So again, like how do you square this? So these are the problems that Einstein finally interprets correctly what's going on. So let's say he has this train car. This train car got this guy inside, and he's got his stopwatch with him, okay? And he's also got this flashlight on the ground that's sending out these beams of light. And there's a mirror on the top of this train car. So we're going to follow a beam of light, and we'll just go just like straight up and bounce it straight down. So boing, just like that. Okay, so that's all fine and good. Okay. Now this guy in this train car, if he can't see the outside world, can he feel how fast the train car is moving? If it's moving, like does he know if it's going 30 or 40 or 50 miles an hour? No, we talked about going back to like August in this class, that you can't feel speeds. You can feel forces and accelerations, but not velocity, right? Now, why am I saying that? Because what if this train car is in motion with some speed v, and there's some guy outside the train car who also brought along his stopwatch, and he's watching this whole situation, and he sees the beam of light. Now, the beam of light that bounces up and down. Well, if the train car is in motion, doesn't that beam of light also travel along with the train car? So if the train car goes left or right, point A to point B, before and after. Your flashlight, guy inside, whole deal. Okay. Then the guy outside would say the beam of light actually traveled on a path that looks more like this. Now, my picture is greatly exaggerated, but guys get the idea. It's going to travel on a diagonal. Okay? And remember, the guy inside has no way of feeling what V could possibly be. Like, you only detect it relative to something like an outside tree or something, right? Okay, so these guys see the speed of light, or sorry, see this light beam travel at different distances, don't they? Guy inside says only one short distance. Guy outside says no, the one a longer distance, one along this diagonal. Okay? But if they break out a tooth wheel and each measure the speed of this light beam, they both agree on exactly what the speed of light is. It's like 2.998 something times 10 to the 8 meters per second. So they get the same speed of light. So let's look at a one-way trip, just like either up or exactly this diagonal. The guy inside the train says that the distance it went was speed times time, because distance is speed times time, right? So you got the speed of light times some time. And the guy outside the train says, well, it went on this diagonal, which is the speed of light times some amount of time. Okay? But you guys see where this is breaking down? I mean, this is the problem that people saw in the 19th century. They weren't quite sure what to do with, but Einstein just goes this one extra step and cracks special relativity. Okay? These cannot be the same distance because the hypotenuse must be longer than the either leg of the right triangle. And to complete this right triangle, because there's a right triangle here, this leg represents how far the train itself is moved, which would be this v times t, right? So, how can these be? Well, if they agree on what the speed of light is, but they disagree about the distances, that means that they must disagree about what other variable? Time. So there's actually two different times going on in these stopwatches. I'll call this T naught and T. So this would be T naught, and this would be, well, just plain T. And the VT would also apply to the outside guy's time, so that would be T too. All right, so this is it's called time dilation, which is if both these guys start from rest and then the train speeds up to some speed v, that time will actually tick differently for each of these two observers. And you can find the relationship between these two times, the guy in motion and the guy in the inertial frame of reference, with Pythagorean theorem. Right? So Pythagorean theorem is what you need for special relativity. So we're going hypotenuse squared is equal to, see, this leg squared plus this leg squared. Right? Wouldn't that be true? Yeah. Now, what I might be more interested in knowing is what is one guy's time in terms of the other guy's time? You know, maybe based on speed, right? Because you need some kind of speed v, speed of the train to make this happen. But what is t in terms of t naught? Right? What is the inertial time compared to the moving time, the dilation time? Right? So you can go through a series of algebra steps. Let me flip my screen over so you guys can see this. Share screen to. Right, so there's Maxwell's equations we were talking about a moment ago. The speed of light is embedded in those, some kind of constant. But here's the Pythagorean theorem derivation. Right, so zoom here. All right, so that first line is the line I wrote, Pythagorean theorem. And then if you do a bunch of algebra stuff, get down to this last step. Here's t in terms of t naught. Okay. And okay, it looks like divided by, see, some square root. Right? That square root in the denominator there is called the Lorentz factor. You switch back over. Sure. Right, so, okay, so skip through some algebra steps, and t ends up being this ratio, t naught divided by the square root of 1 minus v squared on c squared. Yeah. So that's called time dilation. Now, where do I go next? Story. You guys ever heard something called the twin paradox? Twin paradox. If you ever hear that, they're actually referring to this story, but let's take the train car and turn it into a rocket. And the guy's going to rocket around in space at a relativistic speed. Relativistic speed means some significant percentage of the speed of light. And then the two twins come back and meet on Earth, and they disagree about how much time has passed. But you guys see that right here. So one of the twins says like only a year has passed, and the other twin says no, it's been like 10 years. Right? So which twin is which? I might call them like rocket twin and Earth twin. Right? One of these guys ages quickly, and one of the guys says barely any time's passed at all. So to look at that, I want to do some graphs with you guys. Yeah. Yeah. Let's do this. Right, so we got t equals t naught divided by square root 1 minus v squared on c squared. Let's look at time as a function of speed. Time as a function of speed. Now these are their speeds relative to each other. The slowest they can go relative to each other would be 0 meters per second. Right? They're just standing next to each other side by side. Okay. Now, if you run that into this equation, what does that say? Because one of the things that I want you guys to first get out of the class like this is How do you interpret this equation? How do you maybe test for boundary conditions? How do you push it? What kind of information can you get out? There's some really weird, interesting consequences of this. But let's start with something pretty basic. If you plug in 0 for the v, you get, see, 0 squared divided by c squared. So this is 0. 1 minus 0 is 1. Square root of 1 is 1. And t naught divided by 1, well, that would just be t naught, wouldn't it? So there's this point right here, t naught. Okay. We actually showed a really, this actually shows a really important principle in science called the correspondence principle. Correspondence principle says this: if you come up with some crazy new theory about how something's supposed to work, I mean, this probably looked pretty wacky back in 1905 when Einstein published this. Maybe still looks wacky today. Not only should this new theory be able to explain things that old theories could not explain, and there are actually real applications of relativity that I'll get to for a few minutes, but also the new theory should be consistent with everything the old theories were already good at explaining. For example, if you're moving at a non-relativistic speed, say close to 0 meters per second relative to each other, everybody agrees on how much time has passed. T is just equal to t naught. Right? So all of us in this room have the same 1 second per second on our watches. What if you take v up to c, like the speed of light? You guys ever heard you can't reach the speed of light? Nothing can travel faster than the speed of light? Through space is the catch. Right? You can't travel through space faster than the speed of light if you have mass. What does this equation say about that? Well, c squared over c squared is 1. 1 minus 1 is 0. Square root of 0 is 0. Guys, what is anything divided by 0? And it's not 0. It's a define. And on this graph, wouldn't that show up as a vertical asymptote? Now you can plug in lots of middle values, but here's what the shape of this graph is going to look like. You can approach this vertical asymptote. It's going to, time would go infinite. And if you plug anything larger than the speed of light, you would get an imaginary number in the denominator. So, back to that Einstein question of what would it look like if you're traveling with a photon, with a ray of light? By the way, anything that's massless has to travel through space at the speed of light always. Time would become infinite. So if your rocket twin traveling at like 99.999% speed of light, what would you see? You would see out the outside world, like the universe just like flash by like in an instant. Right? So back to this twin paradox, which twin ages, it's been 10 years. That's this guy right here. That's Earth twin. Rocket twin says, I've only been zooming around in space for like maybe a year. This guy said, no, it's been a long time. So yeah, so they have a disagreement about how much time. Now, if this is true, if there's a time dilation, well, there must also be some other dilations too, and I'll show you guys why. Suppose that here we are in our solar system, got our planet, Jupiter, Saturn, all that, right? And we're looking at some distant star, and maybe there's some distant planet that we want to go explore. And maybe it's like 10 light years away. So it's way off in the distance, like 10 light years away. Light years. Okay. So you hop in your ship, and let's say you move at a relativistic speed, like 90% the speed of light, something crazy. And you go, well, from a point of view of Earth-based observer, it would take you at least 10 years to get there if you're traveling almost the speed of light, and another 10 years for the signal to get back. So you wouldn't even get the news until at least 20 years in the future. Oh, it's okay.
I'm confused because in the equation, if you were to have a larger velocity, then wouldn't t be less than t naught because you're dividing t naught by a larger number?
Yeah. Okay. So let's say, for example, what if v is half the speed of light? Because v is bounded between 0 and c. Okay. So it's like half the speed of light. Well, half the speed of light by the speed of light would be half. If you square that, that's like a quarter. 1 minus a quarter is 3/4, right? And then the square root of 3/4, well, it's bounded between 0 and 1. So this whole square root thing is something between 0 and 1. So let's say like a rocket twin time was like 5 years, right? So t naught was like 5 years. If you divide by, say, something between 0 and 1, let's make up a number. Let's say like 0.63, right? Guys, when you divide by a decimal, does that make the overall number bigger or smaller? It does blow it up bigger, doesn't it? Okay. So somewhere over here, it'd be like larger than the original value. Okay. Yeah. All right. So yeah.
Is t naught what the person moving at that speed is experiencing?
Yes, yeah, true. I should mark that out. Yeah, this is rocket twins time. This is Earth twins time. And v is the speed of the rocket, and c is the speed of light. So rocket speed and speed of light, which is 3 times 10 to the 8 meters per second, a constant, universal constant. Nobody knows why it's that number. We just measured it to be that number. Okay. So back to this interstellar journey, we're going to this other star, 10 light years. From the point of view of Earth twin, it would take, of course, at least 10 years to traverse that distance. But if you're a rocket twin and time dilates, you might say, oh, it only took a year. Now, how can it only take a year to go 10 light years? Well, the only thing that would make sense then is that not only does time dilate, but length also dilates. And length follows this setup. A lot times the Lorentz factor. There's another thing it dilates too, which is mass. So mass is equal to rest mass divided by Lorentz factor. Now, what do those graphs look like? Well, this graph, the mass dilation graph, looks almost exactly like the time dilation graph because the equation looks like the same structure. Okay? But what about the length dilation? So length dilation, look at this one. Here, do mass dilation real fast. M compared to V, I'll throw a C on here. It's going to be a vertical asymptote. Here's the rest mass and that, and it's going to end up towards infinity. Oh yeah, so if you were to reach the speed of light, your mass would become infinite. Now, if you're along for the ride with Rocket Twin, you wouldn't notice any of these weird dilation effects inside the ship. You don't notice, the clock on your wall looks the same, your mass feels the same, length feels the same, but an outside observer would notice something weird like this. Actually, this graph right here that I just knocked out, this is something that particle physicists over at CERN and over in there's this huge synchrotron that runs underneath the border of France and Switzerland, and they smash atoms together. And they run into this all the time because they speed up these atoms at like 99.9 something percent the speed of light. When they do that, say they put in like 1 gram of hydrogen atoms, they notice that we have like 100 grams of material going around that we have to steer into this circular orbit. So where's all that extra mass coming from? Well, it's this dilation effect from special relativity. But the other graph I want to do is length dilation, which has a little bit of different looking equation. So as a function of speed, length, and this is to explain that whole interstellar journey, like how did Rocket Twin feel like we got to the destination so fast? So if you plug in 0 for V, you get this whole Lorentz factor becomes 1, and L is equal to L naught. And so that's all fine and good. But what if you take V all the way up to the speed of light? Well, C squared is 1, 1 minus 1 is 0, square root of 0 is 0. This whole thing becomes 0. In fact, this is a square root relationship. So if you guys remember from a math class, it's going to take this type curve, isn't it? Isn't it? So if you travel almost at the speed of light, what happens? And this works both ways too. So what do you see the rest of the universe doing? You see the spatial dimension of the rest of the universe go down to 0. And if you were at the speed of light, then there would be no such thing as space. I've heard the case made that if you are a photon, there's no such thing as time because the entire universe just flashes by in an instant. And there's also no such thing as space in the universe because the size of the universe is 0 from the point of view of a photon. Anything's traveling the speed of light. So that's kind of interesting. Right, it's good so far. Now, okay. Now I've only got like 8 minutes left here. What can I tell you guys? Let me do this. I'm going to switch my screen over and run some demos. I think that's the most efficient way to show you guys the rest of the stuff I want to show you here.